As we continue our discussion about the Gibbs energy of reactions, I want to remind you that one of the results that we wrote down earlier looked like this, where we related the differential change in the Gibbs energy to the summation over the various components of the reaction times this extent of reaction parameter, dc, and that this expression in parentheses we actually defined as a new quantity, this delta sub Rg, which I also called the reaction potential. Now, I also want to remind you that dc is something that we can write in terms of the differential change in the number of moles of each component in the system. And so this is true no matter what alpha is, and we've earlier had it as the various labels on this hypothetical reaction. But it's basically the differential change in the number of moles divided by the stoichiometric coefficient. So it basically establishes the proportions by which the various reaction species are going to change as the reaction proceeds. Now, one of the things that is of interest for us is to look at how does the Gibbs energy of the reaction change as a function of this extent of reaction parameter. And we can actually get a handle on this by simply integrating this equation. We've got dg on one side, we've got a constant, well, it's not a constant, but it's actually a function, if you will, of this c on the other side, and look at how, as the reaction changes, how does this parameter, this Gibbs energy, change with it. All right, so what I'm going to do is I'm going to let the parameter c range from 0 to roughly 1. That will represent sort of a molar, 1 mole equivalent of this reaction. And what we'll be interested in seeing is the sign of dg as we go through that, because I'll remind you that when dg is less than 0, we have spontaneous change. And when dg is greater than 0, we do not have spontaneous change. All right, so what would this look like? Well, let me show you a sort of a hypothetical. One can actually work this out for different reactions and get a realistic graph, but I'm just going to draw you a hypothetical graph. So I'm going to graph this function g of c along the vertical axis and this extent of reaction parameter along the horizontal axis. What one typically finds for these kinds of reactions is that it'll start at some point that's defined by the initial conditions of the reaction. It decreases, comes down to a minimum, and then comes back up again and increases. All right, so it's a curve that looks something like this. Now, I'll note that the slope of dg in some sense is negative, or it's pointing downward when I'm out here, and it's pointing down this direction. But I can also think of it as over here pointing down in this direction. So in other words, the spontaneous direction of the reaction is always to go to lower values of the Gibbs energy. And when we get down here to the very bottom of the curve, this is a point, a very special point, at which the slope of this curve is 0. So in other words, this is the point at which this slope is going to be equal to 0. And I think you can probably anticipate what this point means. It basically is the point that designates the equilibrium of this chemical reaction. All right, it's occurring right here at the bottom of this function of g as a function of this extent of reaction parameter. So how can we use this, to learn something special about these reactions? Now, I do want to note, because of the definition of this extent of reaction differential, it's changing as the number of moles in each of the species is changing, and those are all changing according to certain relative proportions. So in other words, we're always going to have something that is following a chemical reaction. It's basically locked in to the different parameters that define the reaction. I also, and just in case you remember this from general chemistry, I want to point out that what we're doing here is in fact the same as the old ICE tables for solving equilibrium problems. The initial point in this case would be the initial concentrations, or the initial number of moles of each reactant. The change would be the change in that reactant, all right, which we can write as the stoichiometric coefficient times the change in this reaction parameter. And then the equilibrium value is the sum of these two, so it would simply be Na0 plus nu A dc. All right, and in this case we're using that plus or minus convention. For reactants this will be negative, and for products it'll be positive. But that's really all we're doing here. We're doing it a little bit more mathematically sophisticated way, perhaps. Perhaps maybe mathematically more obscure way as far as you're concerned. But either way, these are equivalent. So if this is the condition that I need to achieve in order to reach equilibrium, what does that look like? Okay, so let's write that up here. And by the way, this differential is taken, this partial derivative is taken at constant temperature and pressure, and we want to set it equal to 0, but we also know that this differential, if I were to write it out from this expression, basically this differential would be equal to this parameter here. So in other words, this is telling us what the slope of G is at different points in the reaction. So what we're looking for is what value of this will give me 0 when I reach it. So at equilibrium, basically, this is the condition that I need to meet. All right, well, in order to get there, we're going to need to put in some of the results that we got before. In other words, we found that this was equal to a reference term, G0, plus RT times a log of a reaction quotient expressed in terms of partial pressures. And now I'm going to indicate that when this is at equilibrium, this whole expression is equal to 0. All right, so for this equilibrium reaction quotient, we will get 0 for this. This piece here doesn't change. This is a reference point at which all of the reactants and products are present at a 1 bar pressure. All right, so how can we find this reaction quotient? Well, we can simply solve this equation to get this reaction quotient. So I could, for example, put RT log of QP on one side, and I'd have negative del RG0 on the other side. Then divide both sides by RT, and I'd have log of QP is equal to negative del G0 over RT. And then at the end, what I'll end up with is an expression for QP, and I'll again specify that this is equilibrium, and it's going to be equal to e to the minus del R G0 over RT. And since this is at equilibrium, we have a special symbol for that. We call this Kp. So this is, in fact, the relationship that allows us to relate an equilibrium constant to this reference standard for the Gibbs energy change for this reaction. All right, actually rather interesting that all of this comes together quite like this. So what we've defined here is an equilibrium constant using thermodynamics. And I'll remind you that this QP actually, and let's write this out, more as Kp, but Kp now is going to be equal to Pc raised to its stoichiometric coefficient, Pd raised to its stoichiometric coefficient, divided by Pa raised to its stoichiometric coefficient, and Pb raised to its coefficient. All right, and all of this is going to be basically all of this is going to be equal to our equilibrium constant expressed as constant pressures. Okay, and let's forget the stuff I've written over here. All right, so this is the result that we're looking for, and hopefully this does look very familiar to you in terms of the sorts of things that you learned in general chemistry. Now, I want to note a couple of things about this quantity here, this delta Rg0 here. It is determined by the following quantities. It is determined by the definition of standard conditions. So we have arbitrarily chosen 298 Kelvin and 1 bar of pressure as standard conditions, but you could choose a different standard, then you would have a different value for this. All right, it also is determined by the balanced chemical equation. All right, that balanced chemical equation gives us different values of these exponents here. It also comes into play in the definition here of of this del RG. And finally, this is all going to be dependent upon the identities of the species, because that's how we set the chemical potentials for these different species. So this quantity here is going to depend on these three things. But you'll notice that I haven't said anything about thermodynamic variables. Well, the only thermodynamic variable that appears in here is T when I look at the expression for Kp. So what that tells us is that this equilibrium constant is a function only of the temperature. It is not a function of the pressure. It's not a function of the volume or anything else like that. So only a function of temperature. And we're going to be examining that a little bit more in the next lesson. But I think it's worth highlighting at this point that the only way you can change the equilibrium constant is by changing the temperature. And the equilibrium constant that you derive is specific to a specific temperature. But nothing else in that sense matters, only the temperature.